Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 30th, 2025, just about 6 days ago. It systematically investigates the design space of joint embedding predictive world models, proposing an optimized configuration that outperforms established baselines in both navigation and robotic manipulation tasks. The paper is titled, "What Drives Success in Physical Planning with Joint Embedding Predictive World Models?" And as we'll see later, the findings on encoder selection and training objectives offer some really practical guidance for building better physical agents. Figure 1 illustrates the core framework, split into training and planning phases. On the left, the training process uses an encoder to embed video observations into a latent space, where a predictor then forecasts future states based on input actions. Moving to the right, the planning phase leverages this learned model to unroll potential trajectories from a start image. By comparing the predicted final state to a goal embedding, the system calculates a planning cost, which is used to iteratively optimize the action sequence for the real task. So, while Figure 1 outlined the theory, Figure 2 puts it to the test with a counterfactual experiment involving a robot arm and a blue cup. Here, the models must predict the outcome of two different action sequences from the same starting point: opening the gripper and moving up, on the left, or closing the gripper and lifting, on the right. The top two rows show the baselines versus JEPA-WMs and Dyno-WM, which fail to capture the correct physics when the gripper closes. However, the bottom row reveals the author's proposed model. It successfully predicts the cup being lifted off the table in the right-hand sequence, demonstrating a much sharper grasp of physical dynamics. While Figure 2 showed a specific example, Figure 3 quantifies the impact of two critical components, the planning optimizer and the training objective. On the left, the bar chart compares different optimization algorithms. The blue bars, representing the cross-entropy method with L2 distance, consistently perform the best, making it the most robust choice. In contrast, gradient-based methods like atom and gradient descent struggle significantly in navigation tasks like maze and wall. Then, on the right, the plot examines the training objective. It shows that calculating loss over a two-step rollout, rather than just one, yields the highest average performance. Okay. Having settled the optimizer question, Figure 4 turns to the input data and the encoder backbone. On the left, the chart asks whether proprioception, giving the robot internal data about its own joint positions, helps. The orange bars show that it usually does, boosting performance, especially in tasks like maze, where precise localization matters. Then, moving to the right panel, we see a comparison of visual encoders. Surprisingly, the image-based Dyno models in blue and orange consistently beat the video-based versus JEPA models in green and red, with Dyno v3 emerging as the strongest performer. Alright, Figure 4 settled the encoder debate. Now, Figure 5 explores history length and model size. The left chart plots performance against context length. We see a massive jump in success rates when moving from a single frame to a context of 2 or 3, confirming that the model needs past observations to infer dynamics like velocity. However, the right panel shows a different story for scale. As the authors move from small to large architectures, the average performance line stays surprisingly flat, indicating that simply adding parameters yields diminishing returns here. So while Figure 5 analyzed the scaling laws, Table 1 brings everything together for the final showdown. It compares the author's optimized model, labeled hours in the bottom row, against the Dyno-WM and versus JEPA-2AC baselines. Across nearly every environment, from simple navigation in maze to complex real-world data in Droid, the proposed method achieves the highest success rates. For instance, in the wall task, it jumps to nearly 79% success, significantly outpacing the Dyno baseline, which sits at roughly 64%. Wrapping up, two takeaways stand out. Effective physical planning relies less on massive model scaling and more on precise architectural choices, like pairing Dyno encoders with robust optimizers. This provides a clear recipe for building agents that understand physical dynamics without needing expensive video-specific pre-training. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.